Hello and welcome to An Introduction to Thalassemias by Omar the Black Man El Hassan, Alex Yin Yang Chan and Callum Green Giant McKay. Basic introduction to thalassemias. What is a thalassemia? Thalassemia is an autosomal recessive genetic trait that results in malformation of specific hemoglobin subunits, causing mayhem in the body. There are basically 4 types of hemoglobin. Each one is made up of 4 subunits of protein that are attached to heme to make hemoglobin. So the basic 4 subunits are alpha, beta, gamma, and delta. So alpha is normally always present in each variation, and it binds to 2 from either beta, gamma, or delta to make the different hemoglobin types. The most common forms of hemoglobin are hemoglobin A, which is made up of 2 alphas and 2 betas. This makes up 95% of blood. Then there's hemoglobin A2. This makes up 3%, and it's made up of 2 alphas and 2 deltas. And then there's hemoglobin F, or fetal hemoglobin, and that's made up of 2 alphas and 2 gammas. So about the epidemiology. The condition is most common in the Middle East, Mediterranean, Central Asia, India, the Far East and Africa, with the highest incidence reported in Cyprus, a massive 14% of the population. Notice anything? That's right, malaria band. Heterozygosity for thalassemias is protective against severe Plasmodium falciparum, much like sickle cell disease, although the mechanism by which it happens isn't clear. There are hypotheses that have been suggested, for example the hypothesis that thalassemic cells can't pass on the Plasmodium parasite to other cells as easily. Because of its protective nature, there are few places where thalassemias and malaria commonly coexist. The trait was spread to European populations through emigration and slavery. The 2 main forms of the disease are alpha and beta thalassemias, which are on separate chromosomes. Let's talk a bit more about alpha and beta thalassemias.
So there's 4 types of alpha thalassemia, and they split into 2 types, carrier state and clinical relevant forms. The clinical state is where there's no symptoms and interventions are usually not needed, and those are your silent carrier stage and your alpha thalassemia trait. In clinical relevant forms, this is when intervention might be needed, is your hemoglobin H disease and your hemoglobin Barge hydrops fatalis syndromes. In hemoglobin disease, your symptom tends to be milder. This is because there's only 1 mutated allele, while in the latter one, both of your alleles are mutated, therefore your symptoms tend to be more severe. Now looking into a molecular part, the 2 alpha chains are located on chromosome 16, and it goes by the sequence of telomer, setter, and then your alpha 2, alpha 1 gene, and then your centromere. Now looking into the reason why there may be a mutation, the most frequent cause are by deletion, and there's more than 40 plus mutation recorded, and they broadly go into 2 categories, your single gene deletion and your extended deletion. And looking into single gene deletion, this is when only 1 alpha chain is affected. The amount of information deleted depends on the recombination that happens afterwards. In a highly homogeneous recombination, only 3.7 kilobase is deleted, and that is named as a negative alpha 3.7. On the other hand, if it's a misplaced recombination, there will be a 4.2 kilobase deletion, and it's called negative alpha 4.2. Now looking at extended deletion, this is when there's 100 to 250 kilobase deletion of genetic material. This could delete 1 or both of your alpha gene and sometimes the setter gene which is near it as well. Interestingly enough, there's a large amount of housekeeping genes such as DNA repair enzymes near the alpha genes. However, when the deleted patient tends to present with normal phenotype other than alpha thalassemia. There is a few reasons why there's an extended deletion. This could be due to transcriptation, where the N or C terminal branches are deleted on your DNA bases, causing a premature termination of chromosome 16. It could also be due to reciprocal translocation, which is an exchange of material between non-homogeneous chromosomes. Lastly, there's illegitimate recombination, which is not something illegal, but it's when gene modification does not fall into any general categories. Looking into non-deletion causes, there's currently about 30 recorded mutations, and they're usually in two categories, which is your change in start codon from AUG to an amino acid of ACG, or it could be your stop codon where the U is changing to C and amino acid is produced. Therefore, you've got a large chunk of junk after your alpha chain before it actually meets another stop codon. There's various different names for it, for various different ones, and the most common one is hemoglobin constant spraying, where there's a 31 amino acid junk afterwards. Moving on to treatment, people in the carrier state and most people with hemoglobin H disease do not need treatment, although they might be given folic acid to aid with red blood cell production. They are also advised to avoid oxidative drug, as this might cause a hemolytic crisis, at which cases your red blood cell destruction is much higher than production. Hemoglobin transfusion might be needed in such occasions. A aplastic crisis such as a parvovirus B18 infection might also require transfusion. Repeated transfusion will be given to people with severe anemia. Lastly, in those with severe spleen damages, it might be removed surgically.
Now we move on to beta thalassemia, which is characterized by a reduction or absence of synthesis of the beta globin chains. Hundreds of different genetic mutations have been identified in the beta globin gene, which is located on the P arm of chromosome 11. These mutations lead to a reduction in the amounts of hemoglobin A that is produced, and also an increase in the production of hemoglobin A2, which is comprised of 2 alpha globin chains and 2 delta globin chains. However, because levels of hemoglobin A2 are already very low physiologically, the increase seen in them is not enough to compensate for the loss of hemoglobin A.
Beta thalassemia is a spectrum of disease from minor to major. This is the result of the various combinations of normal beta globin genes, mutants which lead to reduced synthesis of beta globin, and mutants that cannot synthesize beta globin at all.
Beta thalassemia minor is the carrier form of the disease, in which a patient is normally asymptomatic and is most commonly heterozygous for a mutant form of the disease, which causes an alteration in the structure of beta globin chains, leading to reduced synthesis, but not a complete absence. The alleles in this category are commonly called beta plus mutants. Beta thalassemia intermedia spans the range of clinical presentations from minor to major. A patient can be largely asymptomatic or can require varying amounts of chronic blood transfusion. The distinction of intermedia from minor and major is in the genotype. Intermedia can take 2 different forms, either homozygous for beta plus mutations, or heterozygous for a mutant allele that causes a deletion of the beta globin gene, and hence leads to a complete absence of beta globin production that would normally be expected from that gene. The mutant alleles are termed beta 0. Due to the heterozygous nature of beta 0 alleles in intermedia, this only results in a 50% reduction in the beta globin chains, because you still have one functioning beta globin gene. Beta thalassemia major is the most severe form of the disease, and is characterized by a lifelong need for blood transfusions and iron chelation to treat the iron overload that can result. Common complications include splenomegaly, which can require splenectomies at a young age, and cardiac complications, which account for over 70% of the deaths caused by the major form of the disease. Now, beta thalassemia can be cured, potentially, by bone marrow transplants, and these are only offered to sufferers of the most major form of the disease. Genotypically, beta thalassemia major is characterized by homozygous beta 0 mutations, leading to an almost complete absence of beta globin chains. All forms of beta thalassemia lead to dysfunction via a common mechanism. Due to the reductions of beta globin, there is an excess alpha globin chain production. The excess alpha globins can't form tetramers and so precipitate. This leads to oxidative damage to the cell membrane and apoptosis.
So what are the clinical signs of thalassemias? Now, there's a lot of overlap in the clinical signs between alpha and beta. Increased risk of infection. There's bone deformities from expanded marrow to keep reproducing hemoglobin. Enlarged spleen. Slowed growth rate. And one key one, which is actually caused by the treatment, is iron overload, hemochromatosis. So in the past, thalassemic patients have been given blood transfusions, and because of the constant blood transfusions, they can't get rid of the iron. And that leads to problems of the organs, especially the heart, as iron is deposited. Diagnosis. So a full blood count is done, and it's also screened for in heel prick test as a child. The screening policy exists in Britain, and there's also an extra screening policy in Cyprus. Go figure. So what's the difference between thalassemias and sickle cell? Because they're quite similar. Sickle cell is a single point mutation where glutamate turns into valine. Thalassemias come in a variety of mutations. There's also the fact that sickle cell anemia causes the red blood cells to take up a sickle shape, whereas thalassemias don't necessarily do that. More often than not, the cells are smaller and less pigmented. So thank you very much for watching our video about thalassemias. We hope you've learned a lot. That was that. Thank you for watching.